All right. So last time, if you remember, we started talking about the calculation of reliability for systems that are in series and parallel. So we basically looked into the very basic system with just like two components being redundant or in series. So we're going to look at more complicated system where we have a combination of both. Just a reminder that why we are talking about reliability in this stage. Does anybody know why we switched to reliability in the preliminary design? So we talked about system life cycle, right? We started from conceptual design, then we went to the preliminary design, and then we talk about reliability. Can you make a guess why we talk about reliability now?
Because I think it helps to find the quality of the system and helps to design how to design the system.
So you can calculate, you can manipulate the system now to achieving to certain reliability and not quality. Reliability is one aspect of quality. So quality can be interpreted in so many ways. But one aspect of quality is reliability, and when you create that functional flow block diagram, that's where you can define the reliability of your system. So typically, reliability prediction and modeling is a part of preliminary and detailed design of your system. That's why we talk about it in between, after the preliminary design and before we go to the detailed design and prototyping. So what we're going to learn now, we're going to learn how we can calculate reliability for a kind of functional flow block diagram. And if you remember, we previously saw this slide where your reliability prediction in a system of components that are in series is basically multiplication of, if I talk about reliability, reliability is going to be the multiplication of all these reliability because they all need to work together. But in terms of calculating the, if I have given the failure rate for a component and I want to calculate the reliability, the failure rate for the whole system is going to be the summation of all the failure rates. And then when you plug that into your equation, then you, which is the exponential model, if you assume that our system follows an exponential model for reliability, then you can plug it into your equation and calculate that. So far, I guess this is something that we have already seen. Any question from this slide? All right. So what is the general approach if you have a more complicated system and you want to calculate its reliability? There are 4 steps, the general steps that we can follow. The first step is to create the flow chart or the functional flow block diagram. And you remember that's a part of the preliminary design. And conceptual design, you have it in a higher level. In the preliminary design and detailed design, you have it more in depth. Actually, most of the design process do the calculation of reliability in the detailed design, where all the components and things are figured out. But you can also do it in the preliminary design as a rough cut estimation of the reliability that you're looking for to dictate what type of components you need to put in place in the next level in the detailed design. So the starting point for calculation of reliability is functional flow block diagram. And then you create, using that, you create your reliability diagram that we're going to see in the next few slides. And then you calculate your reliability, and Q stands for the chances of failure. Basically, it's the complement of your R. R and Q together are equal to 1. R plus Q is 1. So Q is 1 minus R, the probability of failure. And then, because most of the time your system is very complicated, we started reducing the functional flow block diagram or our reliability diagram to smaller systems to be able to calculate, so that we can calculate the reliability of the total system together. So look at this series of the two systems A and B, just to show how this works. I'm going to use the like notes here. Because most of the calculation is already on there and sometimes becomes hard to follow through. So if you have system A and B and they are in series, I show the reliability of A by RA and reliability of B by RB. Now if I show the reliability of system with RS, the reliability of system is equal to? No. It's the failure mode, which is the summation. For a failure rate, that is the summation. But what is the reliability of total system? multiplication of RA and RB. Why? Because A and B have to work together to make the system work. So for example, if this one works with this chance of 90% and this one works with the chance of 80%, what is the chance that the whole system works? It's going to be the multiplication of this two. It's a multiplication rule. So 0.8 multiplied by 0.9 gives you the chances of the system works. Now if I ask you what is the probability of system failure, Q of S would be 1 minus RA, RB. Okay, that would be the probability that the system doesn't work, or basically 1 minus R of system working, reliability of system, which is 1 minus 0.782. So you get 0.28 as the probability of failure in the system. So Q is the probability of failure, R is the reliability. When you look at the complicated graph, you can use either one to calculate the Q of the system, and then using QS, you know 1 minus that becomes the reliability of the system. Or you sometimes go based on RS and calculate it all the way through, and 1 minus that gives you the Q of the system. But you don't combine the two together, because otherwise it's going to be a mess. If you, for some part of the system, you calculate reliability, and for some part you calculate the failure, in the end, you're going to be confused because the scale of the system sometimes is bigger. So in the next slide, you kind of, you see that this is generalized. So basically, if I have, instead of A and B, I have A, some other system, and in the end, let's say you have B, if I want to calculate the reliability of this system, I have RA multiply all the way to RB, right? So I can write that as the multiplication of all of my reliability. So that becomes the reliability of total system. And if I want to write the probability of failure, QS, then becomes 1 minus multiplication of all these probabilities. So for a system that is in series, that becomes the general equation for calculation of the probability of failure, where this multiplication goes from I to, let's say, n, if you have n components that are in series. Now, how this formula changes if I have a parallel component in the system instead of parallel components. So let's look at the two components that are redundant, but they're put in parallel, A and B. This is when you want to have a redundant component in your system. So let's say this is exactly the same component as the above component. So I call it, let's say, A1 and A2. Now, if this one has the reliability of 1, and the R1 is related to component 1 and R2 related to 2, what is the probability that the system works in this case? R2, exactly. So probability that R1 works, or A1 works, or A2 works. And that probability, when we have OR operand, then what is the algebraic sign for it? So if I say A or B, it's going to be plus sign. Plus is going to be, so A plus B. So basically, you're looking at probability of A plus B minus A multiplied by probability of B. And this is true. Yeah, we already saw this part, yeah. This is kind of like repetitive of the stuff that we saw, but we want to go to the general formula for them. Yeah, so probability of A multiplied by B, but then AB, this is true only when you have A and B independent. If A and B are not independent, this condition doesn't hold. But for the most part, when you have redundant component, you assume that the two components are independent. That's the whole idea. Because if they were dependent, then it's no longer any redundant component, right? So in the context of reliability, if the two components, we typically use the idea of independency of the components, and therefore, instead of writing AB, we write them A multiplied by B. But the general formula says AB, and this is when the independence condition is true. That replaces that. So now if that I have, let's say, 0.9 and 0.9, because they're exactly the same parts, what is the probability or the reliability of those two works together? The system works. It's going to be 0.9 plus 0.9 minus 0.9 squared. Now, if you calculate this number, it gives you the total reliability value. So if I want to write a general, another way that I can look into this problem is that when the system fail, what is the probability of failure of this system? So it's going to be 1 minus R1. The first system is going to fail, right? And for the second one, you're going to have the same. Let's say if they have the same reliability. So 1 minus R, the second system also has the same probability of failure. Now, what is the probability of the system fails?
Follow the formula.
So it's going to be when both of them fail together, right? That's the only time the system fails. So it's basically probability of Q1 and Q2. When both of them fails is when the system fails. So this time it's going to be 1 minus R squared, basically, right? Now, what is the probability of the system works? It's going to be the complement of that. So I say basically I can say, if I call this Q of S, if I say the Q of the system failure is 1 minus R squared, then what would be the probability of system works? 1 minus that would be, right? So RS would be 1 minus probability that the system fails, which is equal to 1 minus R squared, right? So if you call this, if the R's were different, then what would happen? So basically, this is called Q1. You can say this is Q1. This is Q2. So I can say 1 minus Q1 multiplied by Q2, basically. Is that right? So basically, this is this equation. I say Q1 multiplied by Q2. And this equation would turn into 1 minus Q1 multiplied by Q2. So the general way of this formula then would be reliability of the system when it's in parallel. It's going to be 1 minus multiplication of Q's, where Q is 1 minus R, basically, the probability of failure. So that's one equation that you would need to recall, where I's is from 1 to N. So for the parallel, and if you look at the PowerPoint, the difference between the previous, so for QS, when you had a series, you said 1 minus multiplication of all RI's. This one is 1 multiplication of all QI's. So there is a difference in terms of, and that's Q and the other one is R. So there is they look similar, but they're different. But I guess the best way is to not memorize any equation, just follow the concept exactly, know which one you're looking. So as I said, you either have to look at the reliability or failure of the system. And let's look at one example. I'm going to draw this example here and walk you through this slide step by step because all the information is given all at once. So in this example, you have two systems that are in parallel. And we're going to talk about low redundancy and high redundancy next time, but this seems like a high redundancy system where you exactly have the same system. The whole system has been repeated here. It's not only one component that you're considering a redundant component for it. So this is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this is your original system. The way that the system like this, you need to look at it, is to divide it into parts. Basically, you start reducing your system by considering blocks. So for example, I can develop one block for this part and call this R9, and then consider one block for this one and consider this R10. Now I can calculate the reliability of 9 and 10, and then using that, my system is going to be reduced to this shape. R9 basically for, let's say, block 9, and you have block 10 that has R10. So you're reducing your system to a redundancy of 2 components, only 9 and 10. Now, what is the reliability of block 9? What is R9 equal to? So it's a series of components, so it's going to be the multiplication of all of them. So you're going to have R1, R2, R3, and R4. What is R10? R10 is R5, R6, R7, and R8. Now, if you want to calculate the reliability of the parallel system, what would be the reliability of the parallel system? Basically, you say either 9 or 10 have to work. So basically, you have probability of 9 or 10, right? Which is going to be R9 plus R10 minus R9, R10. So you can write this as you already have R9, you can plug it in here. R1 multiplied all the way to R4 plus R5 multiplied by all the way to R8 minus the multiplication of these two, basically. So instead of that, you could have used the failure mode and make your calculation slightly easier. So R9 is going to be R1 again to R4 and R5 to R8. Okay, that would be your calculation. And since all the R's are the same in this case, all the R's are 0.9. So you're looking at here is going to be 0.9 to the power of 4 plus 0.9 to the power of 4 minus 0.9 to the power of 8, which gives you 0.8817. So that's how you can calculate this. But another approach would be looking to the same problem, but from failure rate standpoint instead of the reliability, and somehow that reduces some of the calculation, especially when it comes down to here. Any questions so far? You're good? So let's look at the next system, and we're going to solve this one from both reliability, and I think the next slide shows from the failure mode, failure rate analysis. So this one has 1 and 2, 3 and 4 are in parallel. Sometimes we're going to have more than 2, and the condition says at least 2 of this have to work for the system to function. Then that becomes a little bit more complicated because you have to use then combinatorial method to include in this. So the first reduction in this shape for us would be these two. So I named these two as R6. Okay. So then you can replace it in your system as this model now. 1, 2, and reliability, each component reliability is given to be 0.8. So this reliability is 0.8, this reliability is 0.8. What is the reliability for block 6?
Or 4 times 4 is 8.
So if the reliability is 0.8 and you want to calculate the reliability of this component, the reliability is when the 1 minus both of them fail at the same time, basically, right? But from the reliability standpoint, if you look at if you don't want to like go that way, I think this one is based on just reliability. So you know that it's going to be either 3 works or 4 works. So it's going to be R3 plus R4 minus R3, R4. Another way to look into this is 1 minus the probability that both of them fails. Okay, 1 minus R3 and 1 minus R4. That would be the, so if both of them fails, then the system is going to be basically not working, right? So what is the probability that both of them fails? It's going to be failure of this multiplied by this. Which is 1 minus R3 and 1 minus R4. So then you have 0.2 and 0.2. And so there is only a 4% chance that both of them fails. 1 minus that, which is 96, gives you the probability that the system works, right? So then you have 96 right here. Or you can call it R6. This is R2, and this is R1. Now, the next block, the next reduction would be on the top here. We replace that with one block that we call 7, which is parallel to block 5. Now what I need is the probability of 7, and we know that this is a series, so it's going to be the multiplication of all the r's on the top. So it's going to be r7 is going to be equal to r1, r2, and r6. So it's going to be the multiplication of 0.8, 0.8, and 0.96. Now if you have r7, that reliability is equal, I don't have the numbers here, 0.61, thank you. Okay, so if you have 0.61 and this one is 0.8, now you want the reliability of the total system. Again, it's going to be 1 minus probability that both of them don't work, or probability that either of them work, which is probability of reliability of 7 plus reliability of 5 minus R7, R5, which is going to be 0.9228. So that gives you, so that's the reduction, that's the meaning of reduction. So you start from the functional full block diagram, start combining all the parallel and series, and calculate your probability in the end. Now if I want to look at the same problem, but from a different approach, instead of looking at the reliabilities, in the end I want to calculate the probability of failure. And from the probability of failure, we can calculate the probability of basically the system functioning. Right now I can calculate that. So this is the reliability of system, and QS is going to be the complement of that, which is 1 minus 9228. But let's calculate this next in the next slide, and then see how we can come up with the same numbers that we did here. So I'm going to draw the same graph, which is 1, 2, and then you have 3 and 4. And then you have 5 here. Okay. Now let's calculate the probability of failure. So the first reduction, again, is going to be this block that we call it 6. So I replace it here.
Probability of failure, right?
Yes. And now we know the probability of, this is the block 6, and we have 5. And the question is, what is the probability of 6 failure? So when the system here fails, what is that?
1 minus R3. So 1 minus R3 into...
No, so think about 1 minus R as Q. You can directly work with Q's. So you can say Q is the probability of this one fails, Q3, and Q4 is the probability of 4 fails. What is the probability of both of them fail?
Q3 times Q4.
Exactly. So you have Q3, Q4. It's both of them. It's A and B. So therefore, the multiplication is going to apply here, because both have to fail for this to fail. Now, if I have probability of failure of 1 and 2, what is the probability that the whole system here fails?
Q2 into Q3.
No, it's not reliability, it's change.
It's
The
1
formula is
minus probability that none of them working, right? So what is the probability of they are, so basically if the first component fails, the other two components are not going to work because they're in series. But what is the total probability of failure? So remember, for the reliability, we said it's going to be R1, R2, R3, multiplication of this. So what is R1 is 1 minus Q1, right? And R2 is 1 minus Q2, and R3 is 1 minus Q3, right? So this is the probability that the system works. Now, if I want to know what is the probability that system fails, it's going to be what? The complement of that. So it's going to be 1 minus this probability. So it's not like Q1 multiplied by Q2 multiplied by Q3. This is the equation. So you say 1 minus probability that the system works, which is where all three are working. So this is the probability that the system works. And 1 minus that gives you the Q for the, so this part, which we call now block 7, Q7 is going to be 1 minus probability that system works. Basically, system 7 works. That's the probability that system 7 works. Any question for that part?
And the 1 minus is the system not working.
Yes. 1 minus that, it says what's the probability of Q7, failure of 7. Now if I want to calculate the failure of the 7 and 5 system, so you have 7 on the top and 5 is parallel to that, and we want to know what is the probability of Q, final Q, which is the QS I call, the whole system fails, is going to be the multiplication of these two, both system fails. So you have Q5 and Q7. So you're going to have Q5 is this equation. Q5 doesn't have equation, it's just 0.2. And Q7 has this equation. So 0.2 multiply that big term up here gives you the probability of failure, which is going to be equal to 0.077. Now if I want to calculate the probability of system working, so RS would be 1 minus that 0.077. That gives you 0.9228. So this has more decimal here. So this exactly gives you the same thing that you calculated in the previous slide. With the difference that instead of going off of reliability, we calculated based on failures. Which indeed, it doesn't matter which one you choose, but you have to be consistent throughout. If you calculate reliability, go all the way, calculate reliability. If you calculate failures, calculate failures. If you switch between the two, sometimes you might get confused along the way. But you can do it as far as you know what you're doing. Okay. So this next example is kind of partially redundant system. So what does this mean? In this case, we kind of made it a little bit more complicated by adding a conditional kind of combinatorial aspect to it. So we say the system works. So you have a component 1 that doesn't have a redundant component directly, but 2 has a redundant component to 3. And 4, 5, 6, the condition says any 2 are required. So any 2 component, if they work, then the whole system works. Okay, or at least this this part of the system works. So you need 2 out of the 3 to work in that system. Then what is that distribution? If I have n trials, so the number of success in n trials is called what distribution? Binomial distribution. So you're dealing with binomial distribution for calculation of reliability here, and 7 is parallel to all of these. So the first reduction, we typically start our reduction from the part of the system that has the highest number of redundant component. So in this case, we have 4, 5, and 6 here that are redundant. And then you have 7, and that is parallel to everything. Now, if I consider this whole system as one system, I call it system 9, because this is called system 8. If I want to be consistent with this slide, this is system 9. What is the reliability of system 8? Is when both of it, at least one of these works, right, for 8. So how do I write that? As R2 plus R3 minus R2 R3. That's the reliability for that one, right? But what is the reliability for 9? It says 2 out of 3 have to work. So if you remember, for a binomial distribution, what was the equation? Probability of x was x out of n, probability of success to the power of x, and 1 minus p was to the power of n minus x. So if I want to calculate probability that 2 out of 3 working, 2 out of 3, and your p is given to be 0.8 to the power of 2, and 1 minus p, which is 0.2 to the power of 1. And this combination, if you put it in Excel, you get the value, which is almost 0.38. So that gives you the reliability of 9. So the probability that at least 2, or it doesn't say at least, it says exactly any 2. If it said at least, then you have to calculate 2 and 3. Okay, so if you needed at least 2, then you have to go with 2 and 3. But since it says any 2, you just calculate probability of 2. So you have 0.38 for this block. And for this block, you already have the equation. So you have 0.8 and 0.8 minus multiplication of these two. And that is equal to 0.96. And so you have R8 is equal to 0.96, and this is 0.8. Now I can calculate the first or the top part of the graph. What is its reliability? So the reliability, if I call this whole block number 10, then reliability of 10 is going to be the reliability of 1 multiplied by reliability of 8 multiplied by reliability of 9, which is equal to 0.36. Is that 0.36? I have like things that are blocking this. 0.36. 0.36. Let's put 0.36, but you double check this number. Actually would be easy to see if this number is right or not using Excel if you have it handy, so we can multiply these numbers. You have 0.8 multiplied by 0.96 and multiplied by 0.38. That gives you 0.29 actually. So 0.29 is that number, 0.29. So maybe I have to double check this 0.38 here. So there might be some numbers, not some miscalculation, but I trust you guys in terms of doing that part of the calculation and double checking later on. So if I want to now calculate the reliability of the whole system, I have block 10. So our system has reduced to these two blocks. So you have block 10 and block 7, and you want to calculate the reliability of that. And let's say we call it the reliability of the whole system now. It's going to be either of them working. Then basically it's 1 minus none of them working. I can look at it that way. So 1 minus probability that 7 doesn't work. 7 is going to be 0.2, that probability. Probability of 10 doesn't work is going to be 1 minus its reliability. We calculated 0.29. So that value, the multiplication of these two numbers, 1 minus that, gives you the total reliability of the system, which is 0.86. So I assume that there is some miscalculation either here or here. You can double check those, but the final number should be right. So you get 0.86 for the probability of the whole system to work. So that's the reliability calculation. What is the probability that the system fails? The chance of the failure of the system is 14%. Now, if you're looking to increase the reliability of this system, you have to start adding redundant component, right? But which one would you add redundant component to?
The one has highest failure.
Yeah, but then so some of them comes from trial and error, but there are actually systematic way of increasing reliability. One of the things that I want to go over is the system with low and high level of redundancy. So let's look at that. Let's look at that type of system. But any question for the calculation of the previous reliability? Everybody's okay. All right. So let me ask you a question first to explain this, and I guess you kind of get the idea from high and low redundancy. So let's say you have, so component A actually B is redundancy of A, so I name them the same way, so you identify that. And another system is the system where you have A and B like this. Okay, which system do you think is more reliable? Or which one has a high level of redundancy? Or which one do you consider as has a low level of redundancy?
I would say the top one is more reliable.
So for each component or for the whole system?
For the whole system.
So this one we call low level of redundancy. This one we call high level of redundancy. Why? Because here we consider redundancy for each component, as opposed to here we consider redundancy for the whole system. So the whole system is repeated once again here. But in this system, you might have components that are not repeated. So you go by component as opposed to by system. Depending on now what are the critical component or critical function in your system, then you can define whether you want a high level of redundancy. Do you want the whole system to be redundant for that specific subassembly or function? Or do you want to go based on some of the components that are critical in that function to just consider component level redundancy? Sometimes you might have both. So within a system that it has redundancy, you might have component level redundancy as well. So think about cars. So what function in car do you think has redundancy?
The brakes.
The brakes, right? Brakes has redundancy. And what other, can you give a function in car that doesn't probably have a redundancy?
Engine.
Well, we did, so you don't have a redundancy for the whole engine system, but you have redundancy in the component level. And why don't we have redundancy in the engine level? Weight and cost. So there are so many constraints that we have that we cannot consider redundancy in the whole system level. We have no choice than considering redundancy in the component. So one of the major challenges when you think about redundancy is the weight of the product, because the weight is going to always want to be one of the contradictory factors with the speed or other performance characteristic of any mechanical system. So when you want to consider redundancy, you don't just throw in as many redundancy as possible. You just have to find the really critical component that their failure is going to dysfunction the whole system. So when we go to fault tree analysis, we actually can identify what are the subcut system or subsets that gives us failure of the whole system. You can kind of identify a single point of failures and consider redundancy for those. But so that's the overall idea about like considering redundancy in the system. Sometimes you might have bridge system. Give you an example of a bridge system. You've probably seen bridge system in a circuit design as well, where there is a component in between. If you remember what you did with them when you were in circuit design. So this is component 1, component 2, component 5, component 3, and component 4. If I ask you to calculate the reliability of this system, how would you go about this? Is this parallel? Is this series? How would you calculate its reliability? If I ask you, what is the chance that this system works? That's the meaning of reliability, right? How would you go about calculating the chances of, you're seeing it here, right?
Combining C1 and C3.
Combining C1 and 3. Okay, but then what is the role of the bridge, the C5 here? Do you consider these two as parallel right now, or do you consider them as this one series with this one and this one series with this one?
No, it can do both, no?
It can be both, actually. The answer is it can be both. So the way that we calculate this depends on whether system 5 or component 5 is working or not. You can determine the reliability of the system. So basically, a reliability of system in the bridge kind of system, we call it, this is called bridge system. Bridge system. The way that we go about it, we condition based on the working or failure of C5 component or the bridge component. If C5 works, then these basically, you can think about this system. I'm going to draw a new graph for this system based on, if C5 works, you can think about the system as 1 here, C3. Basically, your system becomes 2 parallel system. So C2 and C3. That is the C5. You can, if C5 works, so if it's working, you have 2 parallel system. Now it's easy to calculate the reliability of this system, right? You have 1 reliability for this one. What is R here, reliability? Let's call this system block 1 or block 4, C1, this is C4. Okay, so let's call this one R6, this is block 6, and this is block 7. So you can say block 6 reliability is equal to, so it's the reliability, either one of them at least works, right? Or 1 minus the probability that none of them works. So 1 minus R1 multiplied by 1 minus R3. Now, if both of them have the same R in this case, because they're the same component, I can write it as 1 minus R squared, right? So that's the reliability of 6. Let's calculate the reliability of 7. Reliability of 7 is going to be the same thing, 1 minus R, let's say if the R's are the same, squared. And then what would be, so we call this R7 because these R's might be different, and this is R. So just same R squared. So now what is the reliability of total system? Multiplication of these two. Basically you have R of system. If R is the same, then you're going to have 1 minus R squared, right? This is the reliability of the bridge system. Now, if I have if C5 is not working, then what happens to the system? Going back to the previous graph that we had, this is the original system. Now, imagine R5 now is not working anymore. Then the system change into what? So these two are series and are in parallel with these two that are in series. So then your figure or your chart is going to change to these two being in parallel. So you have C1 and C2, then C3 and C4. Can we project the handwriting in both the screen? Thank you. So right now, what would be the reliability of the whole system? The reliability on the top would be R squared, if both of them have the same reliability. And this reliability in the bottom also is going to be R squared, right? Because these two are series, R multiplied by R multiplied by R. Now, what is the reliability of the whole system? 1 minus the probability of both of them are not working, which is going to be 1 minus R1 minus R squared, right? Multiplied by R
squared again, right?
Yeah, R squared again. So this is going to change to the reliability of system is going to be 1 minus R squared to the power of 2. You see the difference between the two equations? Okay. Now, what would be the final equation now? So once we calculated with Q5 working, once we calculated with Q5 not working. Now, what is the final system reliability?
So we can find, for C5 if it's working or not.
Okay, so the question is what is the chances that C4 actually working? What is the reliability of C4? Because if you have the reliability of C4, then we can say with X% of the time, this is going to be the reliability with 1 minus X%, this is going to be the reliability. So if we have the reliability of C4, then we can condition our probability based on the probability of the component 5. So the way that the final equation is going to look like, because I need this part, so I'm going to take it off and put it here. So the final reliability for the system is going to be conditioned over the reliability of 4. So basically you say R5 multiplied by probability, R5 working basically. So R5 shows the reliability of 5 working. Multiply that probability that system works plus 1 minus R5, which is the Q5 basically, probability of the failure, multiply the probability that the system works. So basically when it fails, you get the reliability of the system, which we calculated previously, and we calculated this part too. We just need to condition it based on that R5. So basically the equation turns into R5 multiplied by the term 1 minus R squared, that is squared, plus 1 minus R5, which is the probability of its failure, multiplied by the equation that we calculate when R5 is not working, which is squared here. Okay, that becomes the probability of the system working in general. But again, as opposed to memorizing all these equations, it's always good to understand what happens, because the system might get more complicated or less complicated depending on the way that it works and where the bridge exists. One thing that you need to know is the reliability in a bridge system depends on the probability of reliability of the bridge component. So if the bridge component works, you're going to have a parallel system. If the bridge component is not working, then you're going to have series of the two parallel system. Series and parallel, like a combination of the two. But all right, so that covers the calculation of reliabilities. But then there are, so going back to the PowerPoint, where there are some problems when we calculate reliability. Sometimes our reliability is changes. Our calculation doesn't hold because some of the rates and number that you calculate based on off of the book, we calculate some of these rates from a book. It's going to change based on the number of, let's say, the number of hours something has been stored prior to its usage. So a lot of military stuff have a really long period of, especially the ammunition, they have a long period of storage that is going to hugely impact the reliability. So, or sometimes because of fatigue or other thing, the rate of, let's say, failure changes. So how we can defeat, there are two concerns when it comes to redundancy, is how we can defeat the redundancy, and you have to be cautious about that. This equation refers to the thing that can possibly happen to kind of compromise the redundancy that you have considered in your product. So you might think that by considering redundancy, you've already taken care of failures, but there are things that can defeat redundancy, and you have to take them into consideration to have a reliable product. So what are those defeaters, and can single events defeat redundancy? So if I have two components that are parallel, and I'm considering if one fails, the other one is going to take over, what is the chance that both actually fail? What are the events that causes both to fail? To give you an example, the power distribution in the US is kind of an interesting example that sometimes when a single line fails, because the load gets kind of distributed through other lines, it put over, let's say, more power on other lines and make them to kind of be overloaded and overheated, and therefore breaks other lines as well. So even though you have redundancy, sometimes it might not work as well because it just might work for a certain amount of time, but after sometimes this whole system is going to fail. So that's why when something happens in the US power distribution system. It's very reliable, but very integrated and very connected. Everything is so much connected that works against the system. I give you the very recent example of 2012, I guess, or 11 in San Diego, where the power, the line between Mexico and the U.S. San Diego went out of service. I mean, there was some issues that it just it stopped working, and then all the kind of power was distributed through other lines and kind of impacted them. So the whole area didn't have power for a few days. And that happened in 2002 when the whole North America didn't have, in the U.S., northern U.S. didn't have power because of overheated things. So basically the root cause of the problem was just overloaded line that kind of, because the lines overheated, they kind of like it developed more kind of belly, I would say. And then they touched the trees, then they started a fire. That line went out of kind of system. And the load from that line went distributed through other lines, and the whole event started cascading. So that became like a kind of domino effect to put all the other system out of order because of overheating over and over again. So the question is that you have to answer is, can you find events as such that defeat redundancies? And what are those things? What is your mitigation plan if things as such going to happen? Some of the examples is calibration error, inspection error, process technician error. These are the things that can happen and kind of defeat the redundancy that you have. If human error for the most part is one of the biggest thing. And that was the case in San Diego and also in the North America incident. So if you read the report, the systematic report that they've written, it turns out like human mistake in both cases has been the root cause. All right, so I'm kind of going to stop here because the rest of this stuff is basically giving you example. I let you read through these information. These are basically the resources that you can get the failure rate from them. So military handbook and U.S. Navy mechanical software.
Are you pointing to PowerPoint?
Yes, I noticed that we're switching to PowerPoint. Sorry. Can we switch to PowerPoint?
Yeah.
All right, so there you go. So that was what I was showing you previously. What are the defeaters and the two questions that I wanted you consider. So how can we defeat redundancy and cancel events? Because when you know those, then you can define mitigation plan according to the things that can happen. So calibration, inspection, process technician error, these are the things that can defeat redundancy. And so if you move on for the rest of this slide, you get the failure rates resources, so U.S. Navy software or the military handbook, or there are multiple resources that are listed here that can help you. This is an example of how typical military handbook for the failure rate works. So for specific parts or for a specific specification, you can look them up and see what is the lambda for them. There are more description. This is just like a snapshot so you kind of understand. So this is for switches or toggles on push button. So for a toggle or a push button, what's the typical failure rate? But a lot of time it comes down to your own company, own product, data collection. So you put, so we're gonna see, given a data, how we can develop our kind of reliability function. So you might not have a specific distribution function, but you have a bunch of data. You put, let's say, your product through a test, and you have to collected a bunch of number about the failure of that product, and now how we can use that toward calculation of reliability. So we're going to see an example of as such that is not based on any pre-calculated numbers. It's merely based on the pure experiment that you run in your company or in your experiment. So I leave the rest of this stuff because it doesn't have much of calculation. It's more like description of different things, and make sure you read it. For example, the dormant failure rates is the one that I mentioned. It could be because of the humidity, temperature, is the storage of your products and some sort of thing. So there are And there are rates that is actually given in these handbooks that can help you modify some of the failure rate. So if something has been in storage for so long, their failure rate is now going to increase by 20% or by 10%. So there are a handbook that gives you instruction for those as well. Or again, you can just go based on experiment. But sometimes it's hard to see the impact of long-term storage through experiment. You might use the handbook for specific things. So for example, an O-ring that has been stored for over a year might have a 1.05, let's say, a coefficient for its failure rate. So it increases by 5% basically based on the time that has been stored. So these are the things that you need to be cautious when it's related to failure rates calculation. So next time, in the next class, we're going to talk about failure mode analysis. Basically how, given a drawing, so in the end of the class, the homework for you guys would be given a sort of drawing. You have to come up with the FMEA analysis, basically failure mode evaluation analysis of the product, and develop some sort of formal document for the process failure and reliability. All right? If you don't have any question.